Hi everybody! Today I will be going over another problem on Leetcode. It's titled Leetcode 121, Best Time to Buy and Sell Stock. It's an easy problem, but it is also a problem that is a reasonable ask. I want to quickly go over the problem description before I delve and dive deeper into the code, the solution, and how to tackle the problem. So let's start from the beginning. We're given an array of prices where the prices at sub I is the price of a given stock on the ith day. And our goal is to maximize the profit generated by choosing a single day to buy one share of the stock and choosing a different day in the future, that is a day that is later than the day chosen of the date of purchase, to sell that share of stock. And we want to return the maximum profit achievable from this transaction, otherwise we return 0. And so if we take a look at example 1, right, we are given a list of 6 prices for 6 different days in the order of 7, 1, 5, 3, 6, 4. And the best output is 5. That is the best profit made from a single transaction, which corresponds to a purchase of a single share on day 2, price equal to 1, and a sale on day 5, price equal to 6, generating a profit of 6 minus 1 equal to 5. Now, in the second case, there is no max profit generatable because the sequence of prices is decreasing from 7 to 4 to 6 to 4 to 3 to 1. So we return a max profit of 0. Now I want to go over why I like this problem. So let me talk about it a bit at a high level. What do I like this? The first is the real world applicability. So whether it's in the finance industry, in tech, or in other spaces, a lot of folks have to think about capital losses, capital gains, and maximizing the profit that they incur on the buy, the sell, and the transaction of stocks and other securities. The second reason being that it's actually a simple dynamic programming problem into hiding. Even though it is DP, it's not the most complicated DP. It's a DP problem that doesn't involve many data structures. The problem can be solved with a stack, but it's better we avoid it. And lastly, the problem really emphasizes backwards thinking. So it stress tests how someone can think about the problem or the input, iterating right to left, so going from the array input backwards versus the other direction, which is left to right, going forwards, which a lot of us are trained to do. Now, let me kind of go into a visual for how to think about the problem. So I drew out here a small diagram with one example with 6 prices, 7, 1, 5, 3, 6, 4, with corresponding borers over each day. And what I want us to take note is that we're really focused on maximizing a single transaction with its given price history. If we take a look at, say, 7, all the way at the left, there's no borer to the right, which really shows any stock transaction or a stock purchase or stock dollar amount that is greater than the value of 7. So the max profit generated from a buy at 7 is 0. But if we take a look at alternative values like 1, 5, and 3, we can actually see that the best profit is at day 4, where you sell when the stock price is equal to 6. The reason being that 6 is the max value all the way observed to the right of every other for each of these days. So for day 1, day 2, and day 3, the max value to the right is 6 on day 4. Now we can ask ourselves, hey, well, from this 1, right, we take a look and we see 2 towers, 5 and 6, and we can ask ourselves, why did we still choose? How did we know to choose the 6 over the 5? The reason being that we're really focused on the max to the right. Because we get to make the choice as to how far out in the future we want to sell, as long as that date is greater than the date of our purchase. So of course we cannot sell at day 0 if we're at day 1, even though that value is greater than us, because the time is strictly less than us. We cannot sell on the same day as us. That would be a no-op, resulting in a value of 0. But we can always sell at any date out to the future, which then leads to the best intuition, which is to go backwards, right to left, and always keep track of the day to the right that had the max, not the day, but the value to the right that had the max value. And we store that notion, and we track, always update that maximum value as we iterate. So say we're at day 5. The max value initially is negative infinity or 0. And there's no purchase doable because we get a negative value. But then when we go to day 4, we take the price history at day 5, we update that max value to 4. We ask at day 4, hey, do I have a capital gain? Clearly that's not a case with the max value, so we skip. We're still at 0. But we go to day 3. But over here we update the max value to a value of 6 now. And we can see, hey, if we buy at 3 and we always sell at the max value of 6, we net the best capital gain possible. So we use this intuition to always track and maintain the running state of the max observed value to the right to note what our best capital gain can be. And we only have to return the best capital gain. We do not have to return the buy date and the sell date for what corresponded to that capital gain. Hi everyone, so let's get back to problem number 121, best time to buy and sell stock. And if you come to my screen editor on the right, I have a very short Python-free program written here. And we have a single method that we're implementing, which is to return the max profit. We're given a list of prices, which are integral quantities, and we need to return an integer as well. Now, the good news about the input is the inputs are reasonable. So we only have 10 to the power 5 prices maximum, and the prices are 10 to the power 4. So we don't have to worry about any weird edge cases with floating point exceptions or input not fitting into memory. All right. So as I mentioned earlier in the problem, the way to really think about this problem is from a very dynamic programming running max-esque perspective, where you iterate from your elements right to left. And as you iterate over the elements, you keep track of the running max through that iteration. And the real reason for the emphasis there is because on day t, we want the max price in price history from day t plus 1 until the last day. Because we only care about transactions where we sell in the future. We don't sell on the same day that we buy, and we cannot sell on a day before. So let's take a look at the method here, where we define the max price to the right, initially to a float of negative infinity. We're going to iterate in a reversed manner through our list, where we will get the index as well as the price at the current index value. So for example, the iteration will resemble something, if I take input 1 here, where prices is equal to 7135364, the iteration will resemble 46351 and 7. All right, so we ask ourselves, if the price that we observe is less than the maximum price to the right, we see, okay, hey, the max, that means that there's a capital gain, because the price to the right is, we have a price to the right that is greater than the current price. We compute the capital gain, which is equal to max price to right minus the price, and then we evaluate the best profit as the max best profit that we've observed and the capital gain. Well, I said here capital gain or loss. It should just be capital gain since the max price to write is always greater than the price. After we do this computation of the current capital gain, if there is a gain, we then go to line 20, where we update the max price to write equal to the max of the current price and the price to the right. So we'll always update the history accordingly. A good example of what this would look like is the following. So I take the same input as provided earlier, 715,364. And if I ask what were the max prices, I would see the following structure: negative infinity, 4, 6, 6, 6, and 6 again. And if we come over here and we ask ourselves in this update, when is the price less than the max price? There are 3 locations this happens. So the 3 locations are at price equal to 1, 5, and 3, where the max price to write is equal to 6. In each case, the corresponding capital gain is equal to 5, 3, and 1, where the best profit among 5, 3, and 1 evaluates to 5. The good news about this method is that we've defined is that the time complexity is always linear. It's O of n, where n is the number of price points in price history of the stock. And the other good news is that there's only a single pass for the input, going from right to left. We don't have to go through the input multiple times. Additionally, the space complexity for this problem is reasonable, because whether it's explicit space or implicit space, it's constant. The only space that's updated is the best profit, the max price to write, and a couple of other locally scoped variables. Additionally, it's implicit call stack space because the method is iterative. It is not recursive at all. Alright, so that's my wrap on this problem. I hope you guys found it super helpful, and please leave a like or a comment if you have questions or if you want to further understand the problem in depth. Thank you so much.